Guardian, that was the controller that I was studying with, and by now they are newer, but they still they have the same component. It basically doesn't really change. We have the central processing unit as one component, and then we have detachable or attachable modules, and they can have different functions. For example, here we have a communication module and we have an I/O module, and we can have lots of these I/O modules just stacking. Coming to so basically, you have the control system and you add the amount of I/Os that you use that you need to solve your automation task. And usually it's like if you have a lot of the I/Os, then you probably need a bigger CPU in the end because the automation task gets bigger. But yeah, mostly the cost of an automation system is actually driven by the amount of I/Os that you have. So in oil and gas industry, we basically always if you wanted to know how much an automation system costs in 30 seconds or whatever, you ask how many I/Os do you have, and then you just multiply that and say this is the amount roughly. And it worked pretty well. So this is like the driving factor of how much the automation system in the end costs. You can add them flexible, and you can add them directly to the CPU, or you can add them remotely. So that's just like if everything is attached to the CPU, then you have long cables in the automation system to each and every sensor. So you might pack some of the I/Os and move them nearer to the actual sensors to reduce the cabling effort. And then have a communication cable connected to the remote I/O. For the CPU itself, it doesn't really see any different. It sees only I/O, whether that's locally or remote. It doesn't care. It's all just available resources in the system. You don't have to do anything for that. Then we see that they have some indicators, and they have an external memory card, and they have a mode selector. So here you can basically just start and stop the system. By now, actually, these are not switches anymore, they are keys, or they are virtual ones, because you don't want to have someone going around in your factory and stopping the system. So by now it's a key switch, or it's a digital, just like you have an RFID chip or whatever to switch on the system. Only if you have the permission to do that. And you have the memory card where the program is stored. So there's the logic stored and controlling the system. Not the state, so not the running information, but the program to actually execute the control of the plant from the ground up. And if one of these modules fail, you can actually unscrew them and then replace them quite easily. Even all the cables here, so all the sensors, they are on a separate board inside, and you just unplug that and you can replace the module, put it in, and plug in all the cables back at once. Or you can also replace the CPU, you take out the memory card, you put it to the new CPU, and you start the system again. It's because mostly these systems, they are working somewhere in remote locations, and people there know how to actually use a screwdriver, and that's it. And if you need more than that, then you have to actually fly an engineer to that site. So we had at ABB, we had a factory far in the back of Russia, and they had to change some of, it was just changing some of the names on some of the displays were not right, and yeah, then you have to fly an engineer to that system to just change these names on the screen. It's I don't know, it's probably €1,000 per letter that they change in the end. It's crazy. But that's why remote support would have been good in this case, but it didn't work. So what we have is this gap between the people running the plant, they are usually not very educated, and then you have like people maintaining and supporting it, and they are not running the plant, the people working in the plant, they are not very well educated, and you have the maintenance people from the outside, and only they know how to work with the system. And you need power supply to just run all that. Power supply usually is 24 volts, so that's the voltage that an automation system typically uses. And yeah, then you have some LED status bar, but that just says power is okay, system is running, system is stopped. Then there's the running gag about this memory card. The memory card, actually, if you look at it, it looks like a normal SD card. You can buy them from Siemens still for these old systems. They cost about 300 to 400 euros currently, and they have like 0.5 megabyte of space on it. I mean, that's when they created these cards, 0.5 megabyte of space wasn't like super. No, it was just a very very small amount of memory, even at that time. But it wasn't like today where you have gigabytes in every card by now, basically. The thing is that you can still buy them. Try to find an old SD card on the IT market. So they produced them 30 years ago, and they still basically have them available. That's why they are very expensive. And actually, if you look in detail, even though they look the same, if you try to use a memory card for a long time, you'll find out that it fails after a while. And actually, the technology inside the card is different, because they have these long lifetime cycles, and the memory card actually works for, or is designed to work for 30 years and not to fail within, I don't know, 5 or 10, because they don't care. Yeah? So that's why also sometimes automation systems are ridiculously cheap, ridiculously expensive compared to the cheap components that you get from the IT. Okay, then we have the behavior of an automation system, and let's look at the standard behavior of the automation system, and that's slightly different than to what you would expect from, for example, an IT or microcontroller system. So at the start of the PLC, all inputs, basically all resources in the systems are set to 0. If you plug in a microcontroller, is there anything set to a certain state? Is the memory set to a certain state? Or you will know that? No. So the memory actually is completely random. It's just in the random state while powering it up. There's zeros and ones in it, and that's it. But it's completely random. Then you have the storage part, which is the flash or the storage where you have the program in, and that gets then copied to the memory, and there it needs to create all its data. And if you can see, you can easily do that, like access data outside, like with a pointer outside of the memory you specified before, and that's where you can just read random data, complete garbage. And in a PLC, actually at the beginning it really writes zeros to each and every memory cell to make sure that it has a distinct state. And the microcontrollers don't do that because it needs time to actually write all the memory cells, and each and every boot time that would take time. And for example, these big computers here, they have so much memory. If they would write zeros to the whole memory, that takes minutes in the end, and they won't do that. So that's why you just start them in the state they are, and then you have to initialize all the memory on the fly. Here you can be sure that it's actually set. With peripheral components in the microcontroller, usually they are set in the startup process because they like set certain registers to say whether hidden as an input or an output, and whether it's connected to a, I don't know, ADC or an analog converter or whatever. So the microcontrollers, they are only partly configured during startup. That's different. Then we actually start the system, and then we have this image of input from the inputs, and the image of input means that is also very different and it's also different in thinking. That it was when I first worked with an automation system, that was like the main challenge for me as an IT guy, because the system at the beginning takes a snapshot from all the inputs that are available and copies that to the image of inputs. So if you read something from the input, it's not the current value, it's the value at the beginning of the cycle of the PLC. Okay, that's what you work on. So you only work on the image of inputs, you don't work on the inputs directly. If you are in a microcontroller, you read the register from a pin and you get the current value. You know? Let's say with a very, very slight delay, but it's basically the current value. For control systems, it makes a lot of sense to do it like that, because the inputs, they might, as I said, there might be local inputs, there might be remote inputs, there might be a lot of inputs, like the big FPSO ships in the oil and gas industry, they have around 300 to 350,000 IOs, and if you just like read them in one cycle, that would take time. So what they actually do is, this process is way more complex. They usually, the automation system sends out a clock to all the I/O components and synchronizes the time. And then it says the next cycle begins at that timestamp, and then all the IOs and everything samples their IO information at that timestamp. And after they sampled their information, the system actually starts to collect all the inputs and then copy that to the image of inputs. So that image of inputs is actually really a snapshot in time of all the of the distributed system state. And in a microcontroller, when you go through that in like your C programs line by line, you would have like you ask one input after the other and not a snapshot in time. So creating that snapshot in time is some kind of effort, but it's done in the background and you work on that snapshot in time. The reason is it makes it possible to do like online changes, and then with the next cycle start with a new program, because in the microcontroller, if you work on IOs and it's always slightly off by the timing, you don't actually know when to start with the next cycle. It makes life harder there to change the firmware on the fly. And also in control systems, I don't know if you had control systems so far, then you have like dead times in the control loop, and if you exactly can specify the dead time in the control loop, you can actually like optimize your control strategy. And here you have exact dead times between this input and output, because it's a snapshot in time. So here we have the same, just the other way around. You write to the image of output, so everything you actually say that the output should change, it doesn't change immediately. changes at the end of the cycle, and then the I/O system says that the output should be valid at that timestamp, and then it's first the information is distributed, and then at that timestamp the I/O changes. So you work on a virtual input, you work on a virtual output in a PLC system, and they are a snapshot of the beginning, and they are only transferred at the end. And this is why, like, students have the code write 1 to output 1, and then write 0 to output 1, and then they are in this line up here, and they say, the output is not working, it's not changing to 1. Yes, the image is changing to 1, and then in the next line it's changing to 0, and at the end of the cycle it stays at 0. So it doesn't change at all. So that it's just a bit different mindset compared to the embedded systems where the output typically changes immediately. Okay, keep that in mind. Yeah.
How fast is the cycle, average?
The typical I/O cycle, or the typical cycle time is 10 milliseconds. That's what, or between 1 and 10 milliseconds. That's what the typical PLC systems work. If you have motion control applications, they are faster. They go down to the fastest control cycles are in the terms of about 25 microseconds. But for example, in the oil and gas industry, if you have like temperature control of a big storage, yeah, it's okay. That is a cycle time of 15 minutes or whatever. That's okay because it does not change very fast. So it depends a bit on the application, but typical in the factory automation is between 1 and 10 milliseconds. Okay, so that's your program here should be executed within this 1 to 10 milliseconds. So if you add like a while loop to the system for infinite time, it would be bad for sure. You can't wait for keystrokes in here because you can't not block the system. So that is the next difference then while programming, besides working on the inputs and the outputs. If you create your logic, the logic must be non-blocking. Because if you block the system, then you break the cycle. That's, for example, also the reason, like, if you write to a database which is not real-time capable, you basically have to write information to a buffer, and then you can ensure that you can fill the buffer within a certain time, and that's possible within a cycle. And then there must be like another task that then moves that buffer information to the non-real-time database. And in the end, it just has to be like fast enough before the buffer overflows. But this here is the real-time the real-time cycle in the PLC, and basically at the end you start at the beginning again automatically by yourself. So when you program in C, you have this main function, and inside that main function there would be a while loop, that is this while loop, and then I will tell you first read the inputs, at the end write the outputs, and in between write code that is non-blocking, not blocking the while loop. That would be like the scenario when it comes to embedded system to have a similar outcome. But this is due to the fact that we have an operating system running on the PLCs, and they support this type of control execution. Automatically taking the snapshot of inputs, creating the outputs, and in between executing the code, and they then do the cycle again. Okay. So for today I would just say that's enough for the introduction. If you have any questions, or if you like for example, want to work on your own, like try out things at your home, for example, you can have a simulated environment for PLC programming. We use the TwinCAD environment from Beckhoff, which you can download anyways for free, and then run it for 3 days, I think, and then you like have to re-enter the license every 3 days, but that's how we use it as well. So it's this 3-day license cycle is basically, it's not production ready because you would have to re-enter the license each and every time. And we have the Siemens system, and the Siemens system, if you want to have that installed on your machine, you can come to my lab, and we have keys to work with the TIA portal for 1 year for students. So basically all of the function of the TIA portal are then available, and you can program a virtual PLC controller. And I also have a simulation called, like there's a very small simulation in the PLC controller already. There you can see the I/O and you can like manipulate them by hand. And I have a simulation tool called Factory I/O where you can like build mostly logistic, like parcel handling lines and storage racks and things like that. And it's like a bit like a gaming environment. I'll show you next week. And there you can just build up your stuff and then control that. And there you can also put on a sensor on a conveyor belt, and it will get one once the package comes close to it. And the packages are also simulated in terms of falling down from the conveyor belt at the end and things like that. But it's more like a gaming environment. For like real system, simulation, we would use things like from Siemens. There's NX is the CAD system, and they also have process simulators, and there where you can have like the whole. From the CAD system, you get the 3D information, and then you add the sensor and actuator configurations. Then you can attach that to the simulated PLC. Okay, so if you want to do that on your systems, you can do that. The only thing is, I switched to this MacBook here, and now they have M1, 2, and whatever processors in there, and they don't work with the Siemens system anymore. It broke it, so for that I have a separate laptop, because you need an Intel chip for that. Yeah.
What languages is typically used in PLC? Is it going to be, is it proprietary? So Siemens has their own language?
Yes, it is.
Okay.
It's not proprietary, it's a standardized language. There's 6 languages in the IEC in 6.11.31, and in the updated version there's only 5 left. They deprecated.
Is there like one typical one that's used across the industry, or is it?
Well, we'll use like the most modern textual based one.
Okay.
There's graphical based ones as well.
Okay.
Sometimes that makes more sense. But yeah, we'll just use programming language called structured text. And if I would do a project now, I would use structured text program. But most of the PLCs by now, they can actually run external code fragments as well, like C or C++ code, with some restrictions regarding real-time capabilities, but they can do it. Even Python code can do it.
What was the name of the one you mentioned with the 3-day trial? I didn't get it. The software?
The software to...
the one we could try for 3 days.
That you can try for free.
Yeah.
It's from Beckhoff TwinCAD.
TwinCAD.
Yeah. It should also be in the Moodle course, like that's the one that we use for the lab exercise.
Okay.
Because it has a virtual PLC running on on your PLC, on your PC,
Nice.
and that makes it easy. yeah, the only trouble is with the Apple state, because the PLC, they are actually virtualized, and I tried virtualizing the PLC on this one here, and the success rate is very random.
Oh.
So like every 10th time the system actually really starts, and then it works for a while, and then it crashes with nothing, we don't know.
Consistent.
Okay. So then we see us next week. Hopefully next week there will be no strike anymore. And now most of you actually managed to come here, right?
I think most, yeah. There's probably only like 4 or 5 people must have.
Okay, see you next week. If you want to like use the software, come to me. Later, it makes sense to have the software anyhow if you do mini projects. But then you actually know more about
Here, Kevin. Would I be able to read your PLC thing?
Huh?
Would I be able to read your PLC thing?
Yeah, we did this year.
What did you guys actually use it for? Like what kind of system?
There was 2, we did with specific tax, with the controlling arm.
Oh, no way.
We used the ABB for about.
Yeah, I feel like this one's more intact than elsewhere.
I think it was way more fun. Like, CRM, course, was way better.
What was better?
We programmed.
Tomlin. Oh, no. Caitlin did a thing like that on her place.
That was the thing we used. Basically, your system, so you have the codes, and then you can write.
Just like G code? Oh, the one he's talking
But the
about.
demo we used was ladder.
It's not like, it's ladder, got like the stuff that they, it's not like what we did in
It's just yellow
Phase.
bar, and you have right bit. And these positions within the bar.
It's not like what we did in Phase.
Yeah. So we did some PLC. We used ladder, which was just programming this to take a sensor data. So we did ladder.
Yeah, I also use that, like, the very simple logic, I use a simple graphical language like that.
It is pretty simple. We did do some and maybe we
Yeah, so you use the structured text for motion control. Yeah, because there it actually gets very hard doing that with. So is that new or
Since we got on.
because like
My original.
it started like 2 years ago that I saw the first Irish students actually having some programming skills.
Yeah, but this wasn't part of the university. We did a agreement in TAC college before the university was probably.
Because like here, if you study electrical engineering and you don't like focus on energy or high frequency or whatever, but with the communication and automation, you have to do at least one automation class. You don't have to do the advanced ones, but like all of the German students actually that with this course that already heard like one part of that course, they already work with me in the lab. But it's kind of difficult because on the other hand, I have you as a incoming student, and we need to like match the knowledge before.
Yeah, I think in university, like, they didn't really do anything with PLCs much.
Yeah, it's very basic, like.
But with programming, I mean, did you do some programming?
We looked slightly at MATLAB for like one or two lectures, but it was very, very basic. It's like, yeah, on replacement. Yeah. So we had like a placement year where we went to work in industry. Caitlin did a little bit on her placement year, but the rest of us, apart from these two, not really done it before. Especially the mechanical ones as well. They wouldn't have done like any.
Yeah.